All right, so welcome back to Math 202 Vector Calculus. Today's plan, we're going to talk more about polar coordinates and doing double integrals in polar coordinates. Because I just kind of introduced it to you last time. I showed you what the conversion has to be and all that, but we didn't really do very many examples. And I want to walk through that and show you some cases of why we want to do it that way and how much easier things become when we do that. And of course, that will also strengthen our what's going on with double integral stuff. So we're going to do that. And then I imagine we're going to have enough time for us to start into triple integrals and looking at what's going on there. And get ready, spoiler, the same thing, except now we're doing 3 integrals instead of 2, right? So it's not like anything is substantially different. We're just looking now in the 3-dimensional world as opposed to 2-dimensional world, which of course, that's where the issues are going to lie. So that's our goal today. But before we get there, I know there are homeworks that are due tonight. Are there any that we would like to talk about?
The polar coordinate homework is due tonight. Do you want to keep it that way?
I don't know. I'll let you know how I'm feeling about that once we're done with today. My guess is I'll probably go ahead and extend it, but let's just sort of see how today goes, okay?
Okay. I do have one for the other section.
Okay.
5.2.
All right, so 5.2, I see that Seamus put question 6 and Matthew seconded that, so I'll put that on there. And then which one were you looking for, Bradley?
12.
Okay, so I've got 6 and 12 from 5.2. And then Evan wanted to see a couple from 5.3, so numbers 11 and 17. I think that probably sounds good. And then let's see, Ralph, you also put on 7 and 23. We're definitely not going to do all 4 of those from 5.3, but we'll at least do a representative group so that you guys can start seeing how this works. All right. Anything else? Or at least is that a good place for us to start? All right, well, hearing no others, let's go ahead and go take a look at those. So I'm going to pull up 5.2 first. Let me share my screen. All right. So again, I see on my list, I want 6 and 12 for whenever these guys come up. All right, so while we're waiting for my open math to connect with me here. Oh, too late. I was going to give you a bad joke of the day, but we'll save that for later. All right. See, and now of course everyone feels cheated, right? Like, wait a minute, that was going to be a bad joke. I want to hear it. All right, so let's look at number 6. So it says, suppose that one variable x is chosen randomly and uniformly from 0, 3. And another variable y is also chosen randomly and uniformly from 0, 9. So what is the probability that the value of y is going to be somewhere between x and 3x plus 1? Okay, so probabilities. We kind of talked about probabilities randomly, not because we were talking about double integral, but remember the other day when we were talking about modern physics and electrons being in weird places and all that. We talked a little probability. Well, let's kind of use that same conversation here. So basically, if you think about it, since we're given intervals that we're choosing x's from, think of the x and y's that we're picking as points. So it's probably going to be best if we actually draw this on a plane so that we can kind of get a feel for what's going on. So I'm going to go to the whiteboard, but I'm going to do that as soon as I write down the important information here. But let's go to a whiteboard so we can draw this. All right, so if we look at the whiteboard, we're in the XY plane, right? And it says we're going to randomly choose X's that are between 0 and 3 and Y's that are between 0 and 9. So somewhere out here, of course, then would be 3. Up here would be 9. And so we're basically randomly, let's call that the 3. We're randomly picking out things from that rectangle, right? We're picking things out from in here. Okay, so if I were to ask you what are all the different possibilities here, you'd basically say, well, anything within that rectangle, right? It's got an area of 27, so, you know, whatever. Now, when I talked about probability density functions before, you can think of this as a surface that's lying above the XY plane. And it's going to be such that the probability entirely in here would be 1. So its height would be 1/27. Think of it as a plane, a parallel plane, nice and flat. Height of 1/27, so that we get a total volume of 1. Okay, that's not super important to this problem, but I just kind of want to point that out. Now, here's what we do know. We want our y's to be bigger than or equal to x, right? So we're saying, well, what's the likelihood that if we just randomly pick things in here, that y is going to be greater than x? Well, you guys all know the line y equals x. Looks something like that, right? And so if I want to be y is greater than x, which side of that line do I want to be on?
Top.
Yeah, top. I want to be above. So everything that's in this region up here is such that y is greater than x. So if that was the only question, if I just said, what's the probability that y is bigger than x if we randomly choose points in here? How would you answer that question?
Find the area.
Yeah, you'd find the area. You'd go, okay, well, what portion of the whole area is such that x is less than or equal to y? Well, it would be this chunk. So if we calculated the area of that sort of backwards Nevada shape and then divided that by the total area, that would give us the likelihood that x is less than or equal to y. Okay, but we were also told that we want y to be less than or equal to 3x plus 1. So if you kind of ignore the x bit now, we just want to see y is less than or equal to 3x plus 1. We could do kind of the same thing and draw a line for 3x plus 1. Let's make it green. So it's going to have a y-intercept of 1, a slope of 3. Pretend that. Try to make it look a little more linear. How about that? Okay, so that guy is our line y equals 3x plus 1. And if we want y to be smaller than that, we need to be under that green line. So here's the deal. If we want both of these inequalities to be true at the same time, that means that we actually have to be in the region inside that rectangle that is between those two lines. So I'll just kind of color it in here a little bit. So that little pink wedge holds all of the points that satisfy the compound inequality. Right? So if we're just randomly reaching in, grabbing one of those points, the only ones that are going to satisfy this compound inequality are in this little pink region. So before we get to probabilities, how we feeling? Sense?
Yeah.
Yeah.
Yep. Okay. So now what we need to do, well, it's basically figure out what is that area and compare that to the area of the entire thing, right? So our probability, it's going to equal the pink area over the total area. And it's simply just the ratio of these areas because of the fact that they told us that we're randomly picking, right? Everything is just as likely, right? Now, if we had it such that the probability of choosing certain points was more or less than the others, we'd have to take that into account. But this one, we're assuming everything is just as likely. So all we got to do is look at these areas. So the total, that's nice and easy. That's just 27. The pink area, though, this is where we're going to have to use some calculus. So here comes Integration Man to the rescue. So let me replicate this picture, at least as best as I can. And it kind of looks like that. So this was our y equals 9. This is our x equals 3. This is the y equals x, the y-axis, and then 3x plus 1. So let's think about setting this up with Integration Man. So we have two choices. We can do this as a dy dx or a dx dy. I'm going to recommend that we just do dy dx because that tends to be easiest. So let's think about Integration Man if he's vertical. So like over here, there's an Integration Man as he moves. There's a new Integration Man, and then here's yet another Integration Man, right? And so on. So if we do it as a dy dx, is what Integration Man looks like. All right, so if we do Integration Man, let's think head and feet. So what determines his feet?
Y equals X.
All right, y equals always true. You understand why I'm asking if it's always true, right? Yeah. Because if it's not, if it switches, that means we need a second integral.
Yes, it's always true.
It definitely looks like it's always the case, right? If you look at this picture, the original picture is probably a little bit better in terms of seeing exactly, but as Integration Man's walking, his feet are always on that blue line until he runs into the wall. Okay, so that's good to know, right? His feet are always on y equals x. What determines his head?
Y equals 3x plus 1 and y equals 9.
It actually goes two. There's one of them is y equals 3x plus 1, and I see a couple other people putting that in the chat. Good. And so like you look at Integration Man down here, his head's always bumping up against 3x plus 1. But then as soon as he hits this corner, his head now is sitting up on the roof, which was y equals 9. So if we do a dy dx, we're going to have to use two integrals. All right, but then I start going, well, would it be better if he was horizontal?
No.
Right? If turning him horizontal, would we be better? Okay, so Bradley's saying no, and that was a pretty convinced no. Why? Why is sideways bad news?
Because he has 3 different functions on his feet then.
Yeah, you're going to have 3 different integrals because you're going to have like down here, be sideways. His feet are on y equals 0 and his head is on y equals x. Or sorry, x equals 0 and y equals x. But then a little bit further, he's such that his feet are on the y equals 3x plus 1. He's on the y equals x. And then further still, his feet, well, they're still on 3x plus 1, but it's switched to x equals 3. So if we did a dx dy, Integration Man would require 3 different integrals, which is 1 more than 2, which is why I'm not going to do it that way, because I'm a lazy mathematician. Okay, so here we go. We're going to get our area then. We're going to integrate Okay, so the first integral, his feet were on y equals 3x plus 1. Or nope, I lied. His head's on 3x plus 1. His feet are just on y equal x. So let me come back and do that again. So y equals x. Head was on 3x plus 1. So that's the first integral. And then the second integral, his feet are still on y equal x, but now his head was up on y equal 9. All right. So the real question then is, or the last thing we have to answer, is where does this switch happen? What x value makes it so that we switch from head being on this line to head being on the y equal 9? So how are we going to calculate that? There you go. So Victor just says let y equal 9 and solve for x. We're just looking for those intersections. So to find that point, we're just going to take 3x plus 1, and we're going to set it equal to 9. So that'll tell us where they intersect. I think it's 8/3, Matt. When you subtract the 1, you get 8. And then dividing by 3, you get 8/3. All right, so that means for this first one, integration man's going to go from y or x equals 0 up to 8/3. And then the second integral is going to pick up where that left off, 8/3, and go how far? What's the top bound going to be here? Good, Victor just put in 3 in the chat box. That's going to be 3 because that's where this thing ended. Okay, so there are the bounds then for the two integrals that we need to take care of this. So the last thing we need to worry about, and I didn't put anything in here yet, is we need a function to integrate. Now, I know I never mentioned this in class, but I did it on purpose because it's one of those things that you can pick up pretty easily. But yeah, so Seamus, the answer is 1. Yes, you just integrate 1. So why does integrating 1 give you area? Well, check this out. If you just integrate 1 dA, you're integrating dA. Well, what happens when you integrate a differential? You just get that thing. You just get A. So if you ever want to get just the area of a region, you can use a double integral. It turns out that it's no different than doing a integral, single variable integral that you did back in first year calculus, right? Because like check out what happens on this very first step with this first one, right? So the x bounds, we're not touching those yet, but we integrate 1. When you integrate that with respect to y, you get y, right? And then when you do the fundamental theorem of calculus, you just subtract. So you get 3x minus 1 minus x. Well, that's just top minus bottom, which is what you learned when you wanted to find area, right? You take your top function minus your bottom function and then integrate over those distances. So it's not like you're really doing anything. You don't need a double integral to do this problem, basically. You can set it up with a single variable integral that you would get that you do the single or the double. Anyway, so there's that one. Of course, there's a couple more steps on that. The other one, we'll just jump straight to it. Integrating the 1 gets us the y. Put in these bounds, we get 9 minus x, right? Top minus bottom. So there you go. You got your integrals that you need to do. Well, 3x minus, that's 2x, which when you integrate gets you an x squared. So we get an x squared minus x. that needs to be evaluated at 0 and 8/3. And then the other one gives us 9x minus x squared over 2. That you need to evaluate 8/3 and 3. And I'm not going to do any more on this one because A, you know how to do this. B, I'm too lazy to do it with fractions. And C, let me refer you back to B. I'm too lazy to do this with fractions. But once you get this area, slap that over 27, and that's your probability that randomly picking a point somewhere in this region is going to get you so that the y satisfies this inequality. All right, so questions on that one? Does that make sense?
Yes.
We're good. I forget who asked about this one, but hopefully whoever it was is cool with it. Actually, I think this might have been the one that a couple of you said you wanted to see, but we're good. Okay. All right, so let's head off from this one then. And let's go look at the other one. Let's see what I wrote down. It was number 12, at least according to my list. All right, so I just want to make sure that you guys can all see the homework screen again and not the whiteboard. We good? Yep, okay. All right, so this one, let D be the trapezoidal region in the xy plane bounded by these lines. We want to find the integral of 8x natural log of y dA. All right, so this one, it's actually a lot like what we just did, where they're giving us a region and we're just trying to integrate. The difference is that we're not doing a probability now, which is actually kind of nice because that's like one less of a step. And the other difference is that we actually have a function other than one that we're integrating, which means we're going to have to do a little bit more work when it comes to doing the integral. But basically, here's what I'm going to do. I'm going to picture, look at that region, and then I'm going to think about which way is going to be better for integration man. Horizontally, do I do a dx dy? Or vertically, dy dx? And really what's going to determine that are two things. One is the region, and then I'm also going to look at the function and see about integrating. If we start there, notice that integrating with respect to x is going to be super easy, because that's just going to give us an x squared over 2. Integrating with respect to y, not quite as easy, but we do know the integral of natural log of y. I don't know if you remember the integral of natural log. The derivative everybody remembers is 1 over, but the integral would be natural log of y minus y. You get that by integration by parts. But regardless, we can do either one of those integrals anyway. So this is one more where I think the region is going to define which one, decide which way we do it. But if it comes down to it, I'm going to pick integrating with respect to x first, because it's a little bit easier. Okay, so I wrote down all of our lines that are creating our region. So let me again go and share my whiteboard. Let me just clear all this other stuff out. And let's do the same thing we did before. So our region is defined by x equals 0. So that's y-axis. Y equals 1. So that's right there. Y equals x. And y equals 4. Okay, so again, yours may have a different region, right? It might have different lines and stuff that form it, but the region that we're looking at, again, remember they said it was a trapezoid. Well, it's this guy right there, the trapezoid that's formed by these four sides. Before we set up integration man, we good with the shape?
Yeah.
All right. So let me just redraw it here. So this shape, which way does this suggest we do integration man?
Horizontally.
Yeah, I agree. Because horizontally, integration man is going to be such that his head is always on the y equals x, and his feet are always on x equals 0, right? If we had done him vertically as a dy dx, his head is always on y equals 4, but the problem is his feet switch from y equal 1 to y equal x. So the region definitely suggests that we want to do this as a dx dy. And coincidentally, that's what I wanted to do with it anyway, because of the fact that the integral I thought would be easier. Well, it's going to be easier to take care of x first, right? So here's what that's going to look like then. We're going to have the double integral of 8x natural log of y, but we're going to do dx dy. So we are on x equals 0. And where's his head?
X equals y.
X equals y. So we'll put a y right there. And then in terms of the y bounds, how far he's walking, he's going from y equals 1. And he's going to walk his way up until he hits y equals 4. All right, so there you go. So I don't know how far I want to take this. Well, at least do the first one. So the 8x, when we integrate with respect to x, becomes 4x squared. And we need to evaluate that at 0 and y. So we now have the integral from 1 to 4 of 4y squared natural log of y dy, because when we plug in 0, that of course goes to 0. And this is where I'm going to stop because of the aforementioned laziness. But obviously you can just punch this into your favorite calculator or online resource, get the integral. If you had to do it by hand, do you guys remember what you would have to do with this one? What method?
By parts.
Yeah, that'd be parts. Let u equal natural log of y, let dv equal y squared. You know, just pull the 4 out. But integration by parts will get it for you. Anyway, that equals something. I don't really care because I'm not getting a score for this homework. All right, so better for that one?
Yes, thank you.
We're feeling good. All right, so by my count, those were the only ones from this section. So let's go take a peek at the other section real quick. So we'll jump back over. Actually, hold on, I got too many open windows here. Let me start fresh. All right, so let's go back to 5.3. Okay, so now you can get your bad joke for the day. And I don't know if I've shared this one with you before, so if I have, I apologize, but I don't think I've told this class this one. So it's kind of a two-parter, so you got to kind of pay attention. All right, so why did the chicken cross the road?
Why?
to get to your house. Knock, knock.
Who's there?
The chicken. Duh. Okay, so there you go. That was incredibly bad. I actually learned that when she was a substitute teacher. I think it was a 3rd grade class. Shared her that one. So, yeah.
I've got a bad
Look,
math joke, Bruce.
Okay, cool.
Why was the atheist student bad with exponents?
Why?
Because he didn't believe in a higher power.
Nice. All right, I'm definitely going to have to remember that one.
Oh, that was good.
Yeah, I don't think I can use that on the train because I don't think people are going to get it. I mean, no offense to the general population, but but no, that's pretty good. I like it. All right, finally, we're kind of getting here. All right, so my guess though is that these, because we haven't really talked a lot about it, that's why there are a lot of questions coming up here, but that's totally cool, right? We're going to talk about it today anyway, so we can use these as sort of examples. But let's just sort of recall what we have to do anytime we're doing anything in polar coordinates. So like, what are the first things we have to do if we're going to take an integral and do it in polar?
Get it in polar form.
Okay, so we're going to get it in polar form. We need to convert, right? And the conversions are x equals r cosine and y equals r sine theta. Right? So we always need to do that. And then what's the other thing we always have to do when we convert? Let me give you a hint. Remember, you got to talk like a pirate.
Find R.
RDR.
We have to, when we put in our dA, instead of dy and dx, we have to put r dr d theta, right? R dr d theta. So that's what we have to do when we're in that case. And sorry about that, you probably just heard my doorbell ring, but they can not worry about me right now. If it rings again, though, I'm going to have to step out just real quick. But so we got to convert dA, we got to make an r dr d theta. Okay, so those are 2 things we got to do. Now, other than that, we want to just set it up like we normally would. So let's think about this one. It says we want to find the area inside the circle, x squared plus y squared equals 81. That's above the line y equals 6. So we're looking at the area up in here. So if you think back to that, what we were just talking about with probabilities and area, right? We know that we just have to integrate 1 over this region and we'll be able to get our area. Okay, so let's go to the whiteboard. And let's see if we can get this set up. So let me just replicate that drawing. So we're looking at this piece right here, where this is y equals 6. And this one was x squared plus y squared equals 81. Okay, so if we are going to do this in rectangular, we're going to integrate 1. Let's just say dy dx is probably the easiest way to set up integration man vertically. His feet are always down on 6, and his head is always going to be on square root of 81 minus x squared. So let me just draw a little integration man in there so you can see him. Right, so feet are always on 6, head is always on that. I just solved it for y. So then what about the bounds? What x bounds would we use? Or how would we even figure those out?
I guess plug in 6 for y, solve
Yep.
for x.
Exactly, just like we did with that other one where we find intersections. So we'd have x squared plus 6 squared equals 81. So x squared would equal 45. So x is plus or minus 3 root 5. I think I did the numbers on that correctly.
Yeah.
Okay, so this is what it would look like in rectangular. Now, that's great, but we want to do this in polar, right? So let's look at what our conversions need to be. So first of all, our function is 1. Well, 1 in rectangular, 1 in polar, identical. So we don't have to do anything differently with that. The dy dx, though, we do need to change that into an r dr d theta. So always do those two steps. Change your function and change your dA. Okay, but now we need to figure out the bounds on r's and thetas. Okay, so this is something I haven't shown you yet. I haven't shown you how integration man works in polar. So let me just do that for you real quick. So in polar, integration man comes out radially. So let me kind of redraw this picture. And somewhere down here is the origin. All right, I don't want to draw the axes because they're going to kind of confuse things. But think about radial lines coming out from the origin. Right, like there's one, here's another, right? So we have all of these radial lines coming out. Well, integration man stands on those lines. He's lined up with the radial lines. So in polar, integration man, instead of walking, right, walking along, he rotates. And as he rotates, his height changes according to whatever that radial line is.
His girth or his height?
No, his height.
Okay.
His height. He's still like infinitely thin, just like he was before. But his height is going to be changing to whatever that angle is. So like for this specific picture, when the radial line gets out towards the edges here, like think about, say, this one, integration man is super teeny tiny, right? You can barely even see him. And he's going to be biggest when the angle's at pi over 2. When they're straight up and down, he's actually going to be tallest. Okay, but he's rotating his way around and he's changing his height with this radial line, whatever it happens to be. So now looking at this picture, what always determines his head?
The semicircle.
Okay, so that circle is going to be his head, and then his feet are always from the line. Okay, so the question is, what are the equations of the circle and the line in polar? So this is where we need to go back to conversions. So we had x squared plus y squared equals 81. So what is that in polar?
R squared equals 81.
Okay, good. So we can do x squared plus y squared. We've got the fact that that equals r squared. So that'll be r squared equals 81, or r equals 9. So I don't know if you remember this, but in polar, circles are beautiful. Circles are awesome because all you have to do is r equals. So circles that are centered at the origin are just r equals. So that means that the upper bound on this is going to be 9. All right, so there's that. Now, if we go to the feet, they're given by y equals 6. So here we got to convert again. We're going to have r sine of theta equals 6. So again, we need to solve this for r, right? Because we're doing a dr, d theta. So r is going to equal 6 over sine of theta. Or if you'd rather, 6 cosecant. And I would rather because I don't want to have to write a fraction there. So we're using those same conversions, and we're using the same idea of feet to head. It's just the feet and head are determined radially. So before we go to angles, questions on what I did here? Are we okay?
I think so. I kind of get it.
Why
Yeah.
did we not use 9 for r sine theta equals 6? Are those different r's?
Okay, so the 9 was specific to the circle.
Okay.
This r is generic r for y.
Okay.
So that's why this one doesn't have a specific number. In fact, that r, the 6 over sine theta r, on our picture, that would the distance to the line from the origin.
Okay.
Right. So like the length of this is going to equal 6 cosecant theta, whatever theta happens to be.
Okay.
All right. So there are those. So now what we have to do is figure out our thetas. So we basically need to think about what thetas sweep us through this region that we're looking at. So
0
if we were going to talk about lower bound and upper bound, there's going to be some angle here. I'm going to call it theta 1. And theta 1 is the first angle we're going to use. Because if that angle is less than theta 1, like let's say we've got this line right there, notice that this line never actually passes through the region. So there never is actually an integration man corresponding to this angle. Same thing with that angle, or this angle, and so on. So the very first one is going to be this blue line, theta 1. And then every angle from there around the other one, it will intersect our region. So this is the other thing that we have to kind of change our perspective on. With rectangular, we always looked at, like if it was a dy dx, let's say we had vertical integration man, we looked for all of the places vertical line intersected our region. Or if it was dx dy, it was all the places horizontal lines intersect our region. Now that it's dr theta, it's everywhere radial lines, as we rotate, hit our region. So we have to just keep thinking circles. When we're in polar, we need to think circular, 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 which means spinning around. That's what's going on with our thetas, is we're rotating around. Our r's are going out along those axes as we rotate. Right? It's the spokes of the wheel. And we're just going out along the spokes. That's where integration man is. All right, I think as we do more of these, it'll make more sense. But let's see if we can kind of still finish this out. So we need to figure out what is this angle right there. Well, here's where we're going to use some trig. Let me redraw that picture. So, whoops, that's again. That doesn't look very vertical to me.
So because we're not evaluating from the x-axis, we do have an angle up above, right? Like if this semicircle wasn't being evaluated at y equals 6, it would just be from 0 to pi. But since it's not,
Correct.
we have this theta 1.
That's exactly right.
Okay.
That's exactly right. Okay, so here is theta 1. Now we need to figure that out, and the way we're going to do it is we're going to use the point out here that's on our, and let's think about what we know about it. What can you tell me about that?
We could tell you that y equals 6.
Okay, cool. We know the y equals 6. So boom, I'll go ahead and give you that. Can you tell me anything else about it?
We can find x, right?
We could find x, and in fact we did. It's 3 root 5.
Then we can find the tangent, the inverse tangent of that angle.
Yep. But we're going to be sneaky about it. I actually know the length of this blue line. How long is that hypotenuse?
9.
Right, because it's the radius. So I'm just going to jump straight to the, not tangent. There's that. What I know is that the sine of theta 1, is equal to 6 over 9, or 2/3. So if I solve that for theta 1, it's inverse sine of 2/3. It's not a nice angle. It's not one of the ones on our chart that we learned on the unit circle or anything like that, but it's an angle. It's perfectly acceptable. And so that's actually what's going to go down here, because this is theta 1, right? We're integrating from theta 1 to theta 2. So let me rewrite it here. Let me leave myself a little more space though. Hold on. Okay, so this is going to be inverse sine of 2/3. So that's my theta 1. Whew. Okay, so that was, so then this is going to be 6 secants of theta and 9 RD theta. All right, but now I need to know that other angle. So the other angle is over here. Again, be smart about it. Let's use what we know from trig. So we want, this is theta 2. But I know theta 2 is going to be pi minus theta 1. Why do I know that?
Because you're smart, Bruce.
I don't
Thank
know
you.
how to say it. It just is.
It just is.
Yeah.
Yeah, okay, I like that. How do we know? Well, just because it is, right? So Victor is actually getting at what I wanted in the chat box. He said, because it's another quadrant, that we can use reference angles. It's got the same reference angle theta 1, right, from symmetry. This guy's theta 1. So since getting all the way around here would be pi, if we take off theta 1, we're back to theta 2. So But I actually appreciate that you guys are getting to that point where the answer is just, well, cuz what else would it be? Right? So this top then is going to be pi minus sine inverse of 2/3. Put a big old equal sign there. So at the end of the day, basically we have to decide, do we want to do the double integral that's in orange or the double integral that's in green, right? Because those are equivalent. It's just the orange one is rectangular and the green one is polar. This is one where maybe we just wanted to leave well enough alone and do it in rectangular. Because this region doesn't really lend itself to nice bounds, right? You look at these bounds, those are not really all that super. So that's just one of those things. So now, Jesus, very good question. He just put in the chat box. He says, can we go to pi over 2 and multiply by 2? So instead of doing all of this, he's saying, let me make sure I am interpreting this correctly. So you're saying go to pi over 2, so cross this off, and instead put pi over 2, and then multiply by 2. So is that correct, Jesus? Yeah, okay. All right, so the question is, can we do that? Well, what do you guys think? What do the rest of you think? Does that seem good, bad? No clue? What do you think?
Yeah.
Good.
Yeah, that seems reasonable.
It seems like it's
thing-
reasonable.
My reasoning is just cuz.
Okay, so we can go to the, well, yeah, cuz it is, right? Now, again, because I'm going to put words into Jesus's mouth or words onto his chat box. You right, and I think for those of you that are going, yeah, that seems pretty reasonable, it's because the shape is symmetric over that line. And just so you guys know, I just got a pop-up on my screen that says my internet is unstable. So if all of a sudden I cut out, that is why, all right? Or I just, needed to go get another refreshing. But anyway, sorry. So you see the symmetry and you go, yeah, it seems like that should work. Now, you got to be really careful. And I think I've mentioned this. You have to be really careful doing this kind of trick because sometimes it works and sometimes it all comes down to what are we integrating. So it all comes back to looking at the function that you're integrating. And since we're integrating 1, in order to do this, this needs to be symmetric. Okay, so not only does the region have to be symmetric, but the thing that we're integrating has to be symmetric as well. So since we're just finding area, the area is totally good, right? This would be totally fine. But you can imagine, what if this function, instead of being 1, was like x sine of y? Is that going to be symmetric on both sides of this? I don't know. Maybe, maybe not, and we'd have to check it. So in general, I want to warn you against using symmetry, okay, in general. But if what you're integrating is a symmetric function, and when I say symmetric, I mean over the region that we're looking at, then you can get away with it. So this one is a perfectly viable option. Instead, just go up to pi over 2 and double it. Anyway, so good question. And yeah, definitely brought up one of the things we have to watch out for. All right, so now at this point, it's a matter of punching this in your calculator and doing it. But you'll see that actually the first integral is easy. R, we get r squared over 2. Yeah, plug these things in nice and quick. But then we're going to get a cosecant squared, and integrating that can be a little bit challenging. But one of interest, I just want you to notice that you're going to be plugging inverse signs into cosecants, and those things are going to simplify down nicely since cosecant is 1 over sine. Just saying. All right, so how are we feeling about this one?
Good.
Ish. All right, so there's your general process. And we're going to do this for every one of these polar guys. We're going to approach it the same way. Real quick, before we go to the next problem, I want to show you what happens if we do a d theta dr instead of dr d theta. At least what happens with integration man if we do that. So let me just come over to the side here, and I'm going to redraw this picture. Right, so here are our axes. Here was our shape. Okay, so when we did it as a dr d theta, integration man went radially. Well, if you do d theta dr, which is actually perfectly fine. I mean, you can swap those just like before. But here's what happens to man now. Now integration man lies on concentric circles. And his body bends around. Okay, so there would be an integration man for a d theta dr. As we kind of move in closer, he becomes less tall. He's still very bendy though, right? Because he's basically following the circles, the concentric circles. So integration man gets kind of crazy depending upon how we do our integration. Right, so this is one of the reasons why we never do d theta dr, is that it's really, really hard to picture it. And it's also challenging to solve things for theta sometimes. Like, for example, think about just that circle, r equal 9. Solve that for theta. You can't really, right? And the same thing, well, like this other one, if it was r sine theta equals 6, that one we could solve for theta. It'd be an inverse sine. So you could do it that way. We very rarely do because you don't want, it's just hard to picture. And integration man, this hurts his back. He doesn't like doing that.
Yeah, could you imagine doing that?
I know, that'd be pretty crazy, huh? That's why he's a superhero. And just wait till you meet 3D integration man. Triple variable integration man, he's like super, super amazing. But that'll be for a later point. All right, so let's go see if we can apply this to some of those other questions that people asked about. So I'm going to go ahead and jump back to the homework set here, and we're going to look at, what was the next one? Number 11. All right, so again, this one just says we want to evaluate the following integral over region R. So we're integrating 10x. We got our dA, and then we've got our region given in polar coordinates. So let me write these guys down real quick so that I can reference them later. Okay. So let's go to the whiteboard. clear all this other stuff. And let's try this one again. Okay, so we have the double integral of 10x dA. And then we're told that a is given by r is between 4 and 5. Theta is between pi and 7/4 pi. All right, so the very first thing I'm going to do has nothing to do with bounds, it has everything to do with a function. Let's convert that function. So 10x, what's that going to be in polar?
R cosine theta equals 10.
It's going to be 10 times theta. So x is equal to r cosine theta, so I just put that in. And then my dA, we're just going to go ahead and talk like a pirate. R d theta. So I always do that first. I don't care about the region. I just bang that out first. All right, so questions on that before we move on? This should be pretty fast and easy in general. Okay, so now let's look at our region. So first we have r's that are between 4 and 5. Okay, well, let's see. So 4, that's a circle of radius 4. R equals 5, that's a circle of radius 5. So what we get is this washer, this donut, this little ring. So that's all the r's that are between 4 and 5. But then we need our thetas to be between pi, 7 pi over 4. So here's pi. Where's 7 pi over 4?
Down a little bit.
So down here?
Yeah.
Oh, I don't like that.
Okay, then go one quadrant over.
Yeah, go on quadrant. It's going to be over here. This is going to be 7 pi over 4. This one would be 5 pi over 4. So it's always the odd 4. So 1/4, 3/4, 5/4, 7. Just the pattern. All right, well, anyway, so we've got those thetas, which means the region that we're actually looking at is that piece right there. So that's our region. So think about integration man extending himself radially. Like there's an integration man. There's an integration man. There's another integration man. Right? And notice his feet are always on the inner circle. His head is always on the outer circle. So that means my bounds on R are going to go from 4 to 5. And then the thetas that we sweep out are pi to 7 pi over 4. And again, at this point, you know what to do. You can just do your integrals and call it good. All right, so is that okay for that one?
Yeah.
We probably should have started with that one. That was a lot easier than the one we just did. But this is basically a, well, if you watch my video, see I'll put air quotes because this is a rectangular region in polar. And I say rectangular because all of the bounds are constants. But if you fix r's and you fix thetas, you're going to get a chunk of a donut, always. How thick the donut is, that's your r bounds. How much of the donut you're getting, that's your theta bounds. So That's the equivalent of a rectangular piece in polar. All right, so there's that one. Nice and quick, hopefully.
Won't this give us negative values?
It could. So you just said, won't it? Well, let's see. What makes you think that's going to give you negative values?
Well, now I'm second guessing it. But if we integrate the first time, we're going to get a positive sign. Oh, wait, no, we won't, because we're doing it with respect to r.
Okay, so that one, you're going to get r squared over 2. Plugging in those numbers, you're going to get a positive. So that chunk will be a positive number. And then, oh, actually, no, it's r cubed over 3. I lied because of the second r. Still going to be positive because 5 cubed is bigger than 4 cubed, right? And then when we integrate cosine, you're going to get sine. But sine of 7 pi over 4 minus sine of pi, that actually will be a negative number. So, and that's okay. You can get negatives. That just tells us that this surface, it's below the xy plane. So negative integrals are not a bad thing. They're a bad thing if we're trying to get areas or volumes. But you guys have seen lots of places where you use integrals for other things, and you can definitely get negatives. That's totally fine. All right, well, let's go take a look at that other one, the next one, which is number 17, I believe. Let's go see what that guy looks like. All right, so again, the following integral over the region D. And so we got our function. Oh, look at that. It's already in polar, so we don't have to do any kind of conversion. This is just a matter of setting up the proper bounds. Okay, well, the r's are going to range from 0 to 2 plus cosine of theta. And then they happen to give us on a graph here what the graph of 2 plus cosine of theta looks like. It's the green one. But if you look at that, it's kind of that sort of semicircle-y looking thing. It's not actually a semicircle, but it kind of looks like that shape. So that's going to be where we're going to. And we're going from 0 out there. So r equals 0 is just a point. It's just the origin. So integration man is going to go radially from the origin out to that green graph. So his feet are always on 0, and his head is always going to be on that curve, which is 2 plus cosine theta. And then they tell us that the thetas are going to go from 0 to pi. All right, so this one, believe it or not, this is almost like they may as well have just given us the integral written out, because they've given us all the information already. We don't really have to think about this. So let me show you what I mean. Let's go to the whiteboard real quick. I can even keep all this other stuff because we don't need that much space. Okay, so first of all, we were integrating the function. Let me just put that back in there. It was a r squared sine of theta, and then we had our RD theta. Whoops, one too many D's there. Okay, so they just told us our go from 0 out to that curve. So there are the bounds on the r. And then they told us that our thetas range from 0 to pi. Well, there you go. And now it's just a matter of integrating this. So with the r's, when you combine those, right, this is a 6r cubed sine of theta. So integrating with r is going to give us r to the 4th over 4. Put those things in. Now, I will give you this, that when we have to plug that in, we're going to get, so it's 3/2 r to the evaluated at 0 and 2 plus cosine. The 0 is not the problem, right? But what we're going to end up with then is 3/2 2 plus cosine of theta to the 4th times sine of theta. So you might be able to multiply all that stuff out. Let me wave you off of that strenuously. Anybody see a faster way of integrating that than distributing it and doing all the trig integrals? Yeah, Seamus just put in the chat box u sub is definitely where you want to use u sub, because if you let u equal 2 plus cosine, then du is minus sine, right? So we're only off by a negative. So if you were to do that, this then is the integral of negative 3/2 u to the 4th, which is crazy easy. So that would be my recommendation for doing this step. But notice that they already gave us the bounds by saying, well, that this is where the region is. So a lot of the times, especially if they're giving it to you in polar, you can just take the bounds literally off of how they're describing your region. All right, so we good for that one? All right, well, hearing no anything, we'll go ahead and move to this one that you guys asked me about. Let's go look at number 23. Oh, good. I'm glad we got to one of these. Because I was working with somebody during office hours and was asked, oh, are we going to look at any of these kind? And I guess the answer is yes, now we will. But let's look at what this is asking us to do. All right, it's saying we want to find the volume underneath the cone. So they gave us the equation of the cone, but I guess this is the graph of the cone. But we want the solid, the volume underneath this cone, but between these ranges. So they're saying we want z's to be between 0.8 and 4.2. So I guess that's actually not the picture of our cone. Yeah, not at all. Our cone, so since this is 6 minus, the top of our cone is up at 6. So imagine that that's a 6 right there. But they also tell us a D, a region over which we want to look. So let me write all this information down again so that I can transfer it to the whiteboard. All right, so we have Z's between 4.2 and 1.8. And then we're just told our theta, we only have a theta restriction. Okay, so real quick, even before we go to the whiteboard, I do want to point this out. Notice in the D, it says the D is equal to, right? There is nothing about the R's. It's just telling us that the thetas are between pi over 2 and 5 pi over 8. So they're not really giving us a restriction on the R's. However, there will be a restriction on the R's because of the Z values. All right, well, let's go to the whiteboard. So I just clear all these guys again. All right. So let's just kind of look at what we're doing. First of all, since we want a volume, we know we need to do a double integral of our function. Okay, that's our surface. I'm just going to put here a dA, right? So this is, in general, how we're going to do that, how we're going to find these volumes, right? Because we got our upper bound and our lower bound. Okay, so let's look at this region. So first, let's look at the angles. It says we want to be between pi over 2 and 5 pi over 8. All right, well, pi over 2, of course, is straight up. Pretend that that's going straight up the axis. And then 5/8 pi is like over here. Right, this is 4/8, so that's 5/8. 6/8 would be pi over 4, 3 pi over 4, and so on. So there's 5 pi over 8. So those are the thetas over which we're going to be ranging. So when we go and we turn this to polar, our thetas are going to go from pi over 2 to 5 pi over 8. We'll worry about the r's in a second. All right, well, let's think about our surface. This, the polar. So x squared plus y squared, that equals r squared. So we get 6 minus r squared to the 1/2. R squared to the 1/2 is just r. So that cone is actually really nice function. It's just 6 minus r. And then we'll put in our r dr d theta. Okay, so at this point, how we doing? Everything tracking so far?
Yeah.
Yeah? Okay. So now we get to go to the, well, what about the bounds on R? And this is where we're going to use the whole thing they told us about the Z's. They told us that the Z's are supposed to be between 4.2 and 1.8. So if you were to actually look at the cone from the side, okay, so there's our cone, we're basically slicing through this at 1.8 and then up at 4.2. So we've cut off the top of the cone, we've cut off the bottom of the cone. And so we're just looking at this little chunk right here and the area that's underneath it. But we're not going to go forever. We're going to go just until our, whatever our thetas were given. But basically that's what's going on. We're cutting off the top, we're cutting off the bottom. So we're looking at this piece, it's called a frustrum of a cone. So we're looking at that frustrum, and then we're just going to look at the piece in here over our correct angles. So if you were to kind of look at the top there, there's a little tiny circle, and at the bottom there's a bigger circle. Right, those are the cross sections there. And these radii, because we want to do this integral from the smaller radius to the bigger radius. Because if we do the smaller radius to the bigger radius, it's going to give us this piece, right? From smaller r out bigger r. So the question is, how do we figure out what the r's are given these z's? Anyone have an idea?
Plug it back into 6 minus r. Both of them.
Yeah, that's 6 minus r. This is a z equals surface. Well, if we plug those numbers in, that'll give us our r. Right? So like if z is 4.2, we're going to get 4.2 equals 6 minus r. If we have the 1.8, okay, well 1.8 is going to equal 6 minus r. And we can solve both of those things for r. So what do you get for r for those two?
R equals 4.2 and 1.8.
There you go. And this is when you realize that this was a mathematician who was just trying to entertain themselves when they were making this question, because the z bounds are actually the same as the r bounds. Purely coincidental, because those two things add up to 6. But that's the kind of thing that I do when I make exams, right? I have all kinds of little fun Easter eggs in there if you know what you're looking for. All right, well, there you go. Now we are set to calculate this volume. So I'll leave this integral for you to do, but think about how we approach this. This time it was a cone, but what if it was an elliptic paraboloid? What if it was a sphere? What if it was a insert your favorite shape? What would you do differently? What would you do the same?
I mean, wouldn't it just be the same, just different radii?
Well, so you'd still convert. Your surface would just be a different surface, right? Like this is what it looks like for a cone. If it was a sphere, you'd get something like z equals the square root of like 16 minus x squared minus y squared or something like that. Okay, well, do the same thing and do your conversion. Or if it was a paraboloid, like a z equals x squared, or, well, yeah, let's say x squared plus y squared. Okay, well, so that would be z equals r squared or whatever. So the only difference is it's a different substitution because it's a different surface. Okay, so that would change. The dA r dr d theta. And then your r's and your thetas are going to change potentially depending upon what they're asking. Right? So if they're saying, well, we only want the part that's, say, above the xy plane, you'd have to look and see, well, what region does this thing form at the xy plane? Use that to determine your r's and thetas. Or if, like in this one, they tell you, well, your thetas are only going to go from here to here, well, sweet. You already have those bounds. You don't have to worry about trying to picture them. So this process works exactly the same way no matter what kind of surface we've got. We just take that surface, we convert it appropriately in terms of the coordinates, and go. All right, so hopefully that makes a little bit more sense here. You'll see, let me actually go back to the homework set, because for those of you who have not gone this far, let me show you that there's some other ones like this, like, all right, so like here's another one. Find the volume of a solid that lies under this paraboloid. Okay, so that paraboloid is telling us the surface. That's what we're integrating. We're going to convert that. So it's going to become 4 minus r squared. And then it says we want the surface that lies within this cylinder. Well, that cylinder is giving you r. That's giving you the region. So you look at the xy plane, you draw this circle, and that's the region that we have to describe. And then you integrate. Like, let me specifically show you the setup for this one. So let me just write this down real quick so you can kind of see what I'm talking about. All right, so we got that paraboloid, and then we're cutting through with it this circle. So here's how I approach this problem if it's me. I draw two pictures. The first one is the surface. So my surface is a paraboloid. So it looks like that. And this was given by 4 minus x squared minus y squared, which in polar is 4 minus r squared. If you substitute in r cosine theta or sine theta, you'll get 4 minus r squared. Okay, so then here's my second picture. My second picture is the one that shows me my region, right? And they said we wanted a volume under this that was within x minus 1 squared plus y squared equals 1. Okay, well, that's a circle. It's radius 1, and it's centered at 1, 0. So there's my center. It's radius 1. All right, so this picture, you'd have to turn it horizontally or sideways. You have to flip it sideways because it's on here, but in the plane. But this is what I'm slicing through. So if we call this region R, I've got the double integral of my region R of 4 minus r squared RD theta. And now it's just a matter of specifying this region. So I do want to do this in polar because it will definitely make life easier seeing my function. I mean, this function's super nice to go into polar, but this one's not bad in polar. Let me draw some radial lines so you can see where integration man is in some various places. So integration man, he extends out radially. So like here, his head, and there's his feet. There's another integration man. There's the integration man there. All right, so integration man is just going out this way. So his head is determined by this circle, and his feet are determined by the origin. So if we're going to do some bounds on this, I know his feet are at 0. To get his head, I have to look at this equation and convert it to polar. So check this one out. If I FOIL this out, x squared minus 2x plus 1 plus y squared equals 1. The ones cancel. I've got x squared plus y squared. Well, that's r squared. So if I go ahead and write that, I've got now r squared minus 2x equals 1. The x, that's r cosine theta. Oh, actually, equals 0 because the ones cancel. I can factor out that r. So I have two choices. One is r equals 0, and the other is r equals 2 cosine theta. Well, I'm not going to use r equals 0 because that is clearly not where his head is. It's where his feet are. So his head is 2 cosine of theta. So there. And then I just need my bounds. And if you kind of look at how I've got my guy drawn, this can kind of help us if we just want to do this in one interval. He's starting at minus pi over 2, starts rotating to 0, and then up to pi over 2. And it turns out that this one, we only need to go an interval of length pi. If you do from 0 to 2 pi, you actually go around the circle twice. I don't know if you remember seeing that when you talk about polar coordinates, but sometimes there are graphs that you complete faster than a full 2 pi. This is one of them.
Say that again. Why is that going from only negative pi over 2 to pi over 2?
No, so the y is because of the negative r's. Like when cosine goes negative, you get negative r. And do you remember what negative r does in polar?
No.
So if you have a negative r, like let's say we have the point -1 comma pi over 4. So if you wanted to plot that, you think, okay, so here's the line for pi over 4, but I actually need to go -1. -1 means I go the other way, right? That's all a negative means. And so -1 would bring you here. So this is -1 pi over 4. But notice that that's the same as +1 5 pi over 4. That point can actually be represented in two different ways. And so what happens here when r's go negative, those are going to happen when you're over here in quadrants 2 and 3. But negative r's just bring you back to the other side. So you end up going over the circle twice because the r's go negative. It's one of the consequences of how we do polar, that we use a distance and a direction, because there's not a unique way to represent every point. So that's something else you're going to have to watch out for when you do these, is make sure you're not like double counting a circle. And there is no good way of being able to just look at it and know. So what I suggest is, like, you got this circle, just start plugging in some values and see what happens. Right? So let's say we started at 0. You start plugging in numbers. So cosine of 0 is 1. So you get an r of 2. And then you get an r of root 3, and then an r of root 2, and then an r of 1. You get an r of 0. And then once you get past pi over 2, you start getting negative r's, which tells me, oh, I'm actually graphing down here. Until eventually we get to pi. And at pi, you get cosine of -1. So r is -2, which means you're back to where you started. So we actually, if we had started at 0, we at this point the first time once we're at pi. And you can just see that if you plug in the numbers. I would love to be able to give you a always in this form, this is how you tell, but it doesn't exist. It's you got to kind of go with it, right? Adjust on the fly. All right, so a couple of things. One, we're out of time. So believe it or not, we're already done with today. But I'm actually happy. These were good homework questions. They brought up a lot of stuff about polar that I was going to talk about anyway. So we're definitely good there. So number one is we're out of time. Number two, I think it would be a good idea for you guys, just a general blanket you guys, to go back and review polar. To review how polar graphs work, how polar points work, that kind of thing. Because the more comfortable you are with polar, the easier it's going to be to do these conversions. And trust me, there are times when we are going to do conversions to polar because it makes it way easier, or even possible at all. Okay, so review your polar. So that's number two. Number three, I am going to extend this homework. So this section 5.3, yeah, 5.3, that one is going to be due a week from today. Okay, you definitely need some more time to practice with that. So I will change that as soon as we're done here. So 5.3 will actually be due on the 19th at midnight instead of the 12th. Okay, so that's number three. Number four, I will figure out what happened with the quizzes, why only some of you got scores and others didn't. So I will take care of that. I probably won't get to that today, just FYI, but by the next time we meet, I should have that figured out. And then I guess number five is, I'll see you later. Have a good day.
Bye-bye, Bruce.
And I'll see everybody on Wednesday.
Thanks a lot, Bruce.
You are welcome.
Have a good night.